Hello students, Mr. Courtney here. In this video we're going to be talking about measurements and calculations again, and we're going to be focusing on unit conversion and dimensional, and we will define a conversion factor. We will write conversion factors for equivalent measurements or equivalent statements, explain what happens when a measurement is multiplied by a conversion factor, define and use dimensional analysis. So let's start by expressing quantities. If I want to express a quantity like $1, now $1 could be 4 quarters, 10 dimes, 20 nickels, or 100 pennies. Now all these are all expressions of the same amount of money, but what is different is the unit or the scale being used. So we can convert from one to the other. If I want to know how many pennies make $1, I know that 100 pennies make $1. If I want to know how many pennies I have in $500, we can do that. If I want to know how many dimes we have in that same $500, we can do that, because we know how much of each one makes up $1 and what they're equivalent to. Same as if we have a meter, a length of a meter is 10 decimeters, 100 centimeters, or 1,000 milliliters. They're all different ways to express the same length. And again, it depends on the scale being used. If I have a ruler available to me in centimeters, then my length will be measured in centimeters. You can also measure the length in meters. It all depends on the scale available to you and the size of the quantity you're measuring. Let's look at something that's called an equivalence statement. Now, an equivalence statement shows the relationship between two statements, and it shows equality between the two units. What do we mean by this? It means that we have 2.54 centimeters in 1 inch. That's an equivalent statement. 1,000 grams in 1 kilograms. That's an equivalent statement. Because as we can see here, we have different units, but it shows how much of the other unit it takes to make the other one. So we're quite familiar, with this one. 12 inches in 1 foot. 1 pound is 16 ounces. 1,000 grams, in 1 kilogram. So all these are equivalent statements. Again, it tells us the relationship between two statements, and it shows equality between units. Now, in a conversion factor, if I have the equivalent statement 1 meter to 100 centimeter, 1 meter is equal to 100 centimeters. Now, if I divide both sides of the equation by 1 meter, then I get 100 centimeter divided by 1 meter, I get a ratio of 1. Divide both sides by 100 centimeters, 100 centimeters divided by 100 centimeters equal to 1. Now, these two values here, the values that I can use to convert from one unit to another, it shows the ratio of these two equivalent measurements. So 100 centimeters in 1 meter. 1 meter is made up of 100 centimeters. These are what we call our conversion factors. It means I can use this ratio or this relationship to convert from centimeters to meters or from meters to centimeters. And that's what a conversion factor is. It's a ratio of the equivalent measure used to convert from one unit to the other. When you multiply a measurement by a conversion factor, you use it to convert from one unit to the other. You change the numerical value, but the actual size of the quantity measured is the same, because 1 meter is still 100 centimeter. All we're doing is changing the size, the numerical value of the measurement, but we're not changing the quantity of the measurement. It still remains the same quantity measured. Now, when we look at this here, we see that the smaller number is part of the measurement with the larger unit. So we have 1 with the meter. 1 is a smaller number, and it's associated with the larger unit of the meter. The larger number is part of the measurement with the smaller unit. So we have the larger number, which is 100, being part of the centimeter unit, which is the smaller unit. All right, if we were to write the conversion factors for the following equivalent measurements, and I'm not sure if I mentioned this before, but for each equivalent statement, we will have 2 conversion factors, because on one end we'll divide by one of the values and divide by the other value. So if we divide by 1,000 and we divide by 1, So 1,000 grams in 1 kilogram, or 1 kilogram is 1,000 grams. That's what this is telling us here. 1,000 grams per kilogram, 1 kilogram per 1,000 grams. 10 to the 9 nanometers in 1 meter. We have 10 to the 9 nanometers in 1 meter, or 1 meter in 10 to the 9 nanograms. So that these are our equivalent statements, and we've gotten our conversion factors from these. So in dimensional analysis, we use dimensional analysis to solve problems, and we don't just look at the numerical value as you've done so many times before. You're just looking at the numerical value, multiply or divide the numerical value, and you get an answer. We need to also focus on the unit, the dimensions of the measurement. So we have to focus on the numerical value and the dimensions of the unit, of the measurement, sorry. So that's what it is. That's what dimensional analysis is. Now, there are certain steps. If you follow these steps, it will make it easier for you to solve problems utilizing dimensional analysis. The first thing you need to do is analyze. Read your question carefully. Analyze. List the knowns and the unknowns. What do you know? What are you given in the question? What do you want to get? That would be an unknown. Where do you want to go? Then you need to formulate a plan. How to get what you want? What is the goal? How can you use what is known to achieve that goal? That is your plan. Once you've done that, then you're going to calculate, solve for the unknown. And then there's one more thing you need to do when you finish. Evaluate. Does this answer make sense? Is it in the correct unit that I wanted? Does the value make sense? You have to look at all these things. So when you're going to solve problems using dimensional analysis, first you need to analyze, plan, calculate, and then evaluate. So let's look at some examples of just doing numerical values. And it's important that you remember how to work with fractions, because you will be using fractions a lot in dimensional analysis. So we have, what is the product of 1/3 and 2/5? So all we do is that we simply multiply these. We multiply our numerators and our denominators. We get 2/15. When we divide 2 by 50, we get 0.133. We want the product of 1/3 and 3/5. Now, when we have the same number in both the numerator and the denominator, they're going to cancel each other. So that's like 3 divided by 3. So we get 1/5, which is 0.20. Now, if the number we're analyzing is a whole number, like 17 here, what that really means is that the number is over 1. 17 is our numerator and 1 is our denominator. So again, we multiply our numerators and denominators. We get 17 over 4. Then when we divide, then we get a value of 4.25. Now, when we're dividing fractions, as in 1/4 divided by 1/2, when we're dividing fractions, we need to change our division sign to a multiplication sign. And once we do that, we need to flip or invert the number we're dividing by that follows the division sign. So we'll get this. We need to flip a half into 2 over 1, multiply our numerators, multiply our denominators, and then divide them out. And we get 0.5. So that's with numerical values. With our units, so we want to evaluate the units for the following expressions. So we have centimeter times the meter over the centimeter. Now, since we have the same units in the numerator and the denominator, they're going to cancel. So that leaves us with the meter only. Now we have centimeter second times meter centimeter, kilometer meter, megameter kilometer. So what we do now, we look at what do we have in our numerator and denominators that are common. We have centimeter common, so we can cancel those. It's in the numerator and the denominator. Kilometer is also, sorry, meter is also in our numerator and denominator. And kilometer is in our numerator and denominator. So that leaves us with megameter per second. I think I was saying centimeter second before. It's really centimeter per second, sorry. So it's megameter per second as our final answer. because these are the units that we end with. How about this one? Milliliter multiplied by cm cubed per milliliter multiplied by milligrams per cm squared. So we look at what we have common in our numerator and denominator. We have milliliters common, so we cancel those. We also have centimeter, but we have cm cubed in our numerator and cm squared in our denominator. Since they're the same base unit and they have exponents, and we're dividing, we have to subtract the exponents. So that's 3 minus 2, that leaves us with 1. So at least we have centimeter remaining. So that will give us centimeter multiplied by milligram. Okay, so let's look at this question. We want to convert 750 decigrams to grams. So the first thing we need to do is analyze. What are we given? We know that the mass is 750 decigrams. And we want to find the mass in grams. So what is our plan? What is our course of action? How are we going to use what we know to get the unknown? We want to go from decigrams to grams. So that means we have to utilize that 1 gram is 10 decigrams. Once we've done that, now we can go ahead and calculate. We have 750 decigrams. And we're going to use our conversion factor now. We're going to use a conversion factor of 1 gram per 10 decigram, or 1 gram is made up of 10 decigrams. Notice the units that we want to cancel are on opposite sides. We want to cancel decigram, so we have decigram as a numerator, because remember that's 750 over 1, and we also have it as a denominator. So I'm going to divide decigram by decigram, so they cancel. That leaves me with my unit of grams. So we get 75 grams. Now we're going to evaluate our answer. First of all, the answer has the correct unit, so that's good. Then we know that the gram is a larger unit than decigram. The number of grams we expect should be smaller than the number of decigrams, and we do have that, so that makes logical sense. In this example, we're given the diameter of a sewing needle as 0.073 centimeters. We want to find the diameter in micrometers. So our analysis, we analyze. We're given the diameter in 1 unit, and we want to find the diameter in another unit. So we have centimeters as our known and micrometers as our unknown. So our plan is to go from centimeters to meter to micrometers. So we use that logical step. So we convert our centimeters to meter, and then we convert meter to micrometers based on what we know. We also know, we can also use this in our plan, that 100 centimeters is 1 meter, or 1 meter is also equal to 10 to the 6 micrometers. So we start with what we're given. We're given 0.073 centimeters, which is 7.3 by 10 to the minus 2 centimeters. Since I want to cancel centimeters, then that means the next part, centimeters, needs to be as my denominator. So in 1 meter, we have 10 to the 2 centimeters, or 100 centimeters. Now, so we cancel centimeters, we're left with meters. So we've converted from centimeters to meters. Now I want to go from meters to micrometers. Since I want to cancel meters, that means meters need to be my denominator. So we have 10 to the 6 micrometers in 1 meter. My meter is going to cancel because I'm dividing meter by meter. Now we look at our exponents. We have 7.3 as our coefficient, and then we have 10 to the negative 2 times 10 to the 6 divided by 10 to the 2. Remember, when we multiply numbers in scientific notation, we add the exponent, so that's 6 plus negative 2 is 4. And then when we divide, we subtract, so that's 4 minus 2. So that's 7.3 by 10 to the 2 micrometers. Again, when you finish, evaluate. The answer has the correct unit. That's the unit we wanted. Since the micrometer is a smaller unit than a centimeter, then the answer should be numerically larger than the given measurement. And here we have, it is larger than the given measurement. In this one, the directions for an experiment ask each student to measure 1.84 grams of copper wire. If 50.0 grams of copper wire is available, how many students can do the experiment before the copper runs out? So let's analyze. Look at our knowns. We're given the mass of copper available, and we know how many grams of copper each student will need. The unknown would be the number of students that can perform this experiment before we run out of copper. So what's our plan? We need to go from grams of copper to students. That's what we need to find. Grams of copper to students. So if we start with 50 grams of copper, and I want to cancel grams of copper, that means I need to divide by grams of copper. And we also know that each student needs 1.84 grams. So that's 1.84 grams of copper per student. But copper needs to be in my denominator. So that's one student for every 1.84 grams of copper. There we're going to cancel our grams of copper. That leaves us with student, or in this case we get 27.174. Now since we're going to need to round this off because we cannot have 0.174 for students. So the number of students that can complete it would be 27 students before we actually run out. That the unit is correct. At approximately 2 grams of copper per student, then we expect our answer to be somewhere close to 25. Since we're using a little bit less than 2 grams, we expect it to be slightly higher than 25. So it's going to be close to 25, but a little bit higher than 25. In this question, we want to know how many seconds are in an 8-hour workday. So let's look at what we're given. We know the time worked, which is 8 hours. We want to find the time worked in seconds. So our plan would be to go from hours to minutes to seconds. What are we going to use? How are we going to get to our answer? We know 1 hour is equal to 60 minutes, or 1 minute is also equal to 60 seconds. So we can use these. This is our plan of action. This is how we're going to go from hours to minutes. Use a relationship that 1 hour is equal to 60 minutes. Then from minutes to seconds, that 1 minute is equal to 60 seconds. So if we start with hours and we want to convert our hours to minutes, that means I need to be divided by hours. So that's 60 minutes in 1 hour. My hours are going to cancel. I'm left with minutes. Now I want to go from minutes to seconds. Minutes need to cancel, so that means minutes need to be in my denominator. So that's 60 seconds in 1 minute. Minutes cancel, that leaves us with seconds as the unit of our answer. We get 28,800 seconds. Evaluate. Or we can put this in scientific notation. That's fine. 2.8800 by 10 to the 4. So if you want to evaluate this now, we have the correct unit of seconds, and we know seconds is a smaller unit than hours. So a large number of seconds is expected to be in 8 hours. Okay, in this question we're given the density of manganese as 7.21 grams per cm cube. We want to convert the density to kilogram per cubic meter. So this is a bit different to what we've been doing before. Before we've been converting single units. Now we want to convert 2 units at the same time. But the steps will still be the same. We can only convert 1 unit at a time. So we can convert grams to kilograms and then cm cube to cubic meter, or whichever way you choose to do it first. But we're still going to go about it the same way, the same steps. We're going to identify our knowns, identify our unknowns. Then we're going to analyze. We're going to start with grams per cm cube, convert our grams to kilograms, and then convert our cm cube to meter cube. And that will leave us with a unit of kilogram per meter cube. We also know that there are 1,000 grams in 1 kilogram, 100 centimeters in 1 meter. So if we have a cubic meter, that means we have 10 to the 2 centimeters cubed, which is equal to 10 to the 6 cm cube in 1 meter cube. Once we know that, that's our plan of action. That's how we're going to get to where we want. We start our calculation. We start with our 7.21 grams per cm cube. Now if I want to convert grams to kilograms, that means I want to cancel grams. So in my conversion factor, I'm going to use grams must be in the denominator. We know there are in 1 kilogram we have 1,000 grams, or 10 to the 3 grams. Grams will cancel. Now I want to convert my cm cube to cubic meter. And we just said that there are 10 to the 6 centimeters in 1 cubic meter. Now, since cubic centimeter is a denominator, that means cubic centimeters now in our conversion factor needs to be in a numerator. So they're going to cancel each other. That leaves us with kilogram per meter cubed. We're dividing exponents. So 10 to the 6 divided by 10 to the 3, we're going to subtract. So that leaves us with 7.1 by 10 to the 3 kilograms per meter cubed. All right, so that takes us to the end of this portion of this unit. We talked about conversion factors. We learned how to write conversion factors. We looked at dimension analysis, and we solved problems using dimensional analysis. So until the next time, I'm out. Blessings.